Alright, welcome. In this video I'm going to be doing some integrating factor examples, and I think I'm probably only going to have time to do maybe the first half of this homework, but I'll come back and I'll do the second half in a different video. And so just remember, before we even get started, that the thing we're looking for to know that we need to use the integrating factor technique is some sort of differential equation that's like P of t, y prime plus P of ty equals Q of t. Pardon me, I was thinking of something else. And so it's, y prime plus P of ty equals Q of t. And then if we can take e to the antiderivative of p, then we're going to be able to do this technique. So in this case, we're thinking of P of t is 3 over t in this case. And maybe for the first couple, I'll translate it into t's and y's, but then I'll just do it whatever they give me. All right, so I'm going to start with the first one. Y prime plus 3 over t multiplied by y is equal to e to the t over t cubed. Okay. And maybe the first one, I'll take it the whole way through, and then after that, I'll just be kind of proclaiming that the integrating factor is e to the antiderivative of p. But anyway, all right, so I'm going to say, why don't I say, okay, mu times y prime plus 3 over t mu times y is equal to e to the t over t to the 3 multiplied by mu. Okay, and if this is going to work, then this has to be the derivative of mu. Okay, so I'm going to kind of, whoops, I've meant to put all the mu's in red. Let's see if we can do that. That's not really the same once you've already put down black, but whatever. I need that mu prime is going to equal 3 over t times mu. Okay, and what that's going to mean is, if you don't see it like that, you could say, okay, that's like solving y prime equals 3y over t. It's going to be separable. Okay, so basically 1 over mu d mu is going to equal 3 over t dt. Okay, so that's going to be the log of mu equals 3 times the log of t plus c. Okay. Then mu is going to be c e to the 3 log t. Okay, now at this point, probably assuming that, I'm going to assume t is positive because, why not? I didn't say I needed to be prepared for an initial condition in which t was negative, and I gotta think that, the way that the solution is going to come back, it's not going to really matter. So one thing you can do is you could say this is e to the log of t and move the 3 afterwards and take that to the third power. So that's going to be t to the third, c t to the third. Or you could say that you could use that exponent property of logs and say, all right, this is going to be log of t to the third and e to the log of t to the third. Either way, it's going to be c times t to the third. And I'm going to choose c equals 1. So now I've got y prime plus 3 over t times, we're just going to say the integrating factor is mu equals t to the 3. And that's going to be, e to the t. Because I multiplied by the t to the 3 and it canceled. All right. Then I'm going to say, oh, wait a second. This is y prime plus 3t squared equals e to the t. Okay. And it looks like, oh wait, I lost my, mu y prime t to the 3. I was going to say, this does not look like a derivative that got taken using the product rule. And I lost that y also. Okay, pardon me. This was here. But, okay, now this looks like a derivative that got taken using the product rule. So this is the derivative with respect to t of y times t cubed, and that's going to be equal to e to the t. And I'm going to take the antiderivative of both sides, and I get y times t to the 3 is going to equal e to the t plus c. Okay, and then I will get y, my general solution, equals t to the negative 3 e to the t plus c t to the negative 3. Okay, you could call that e to the t over t to the 3 plus c over t to the 3 if you want. It's the same thing, right? Let's do another one. Y prime minus 1 over t plus 1 y. No, 3 over t plus 1 times y. That's going to be equal to t plus 1 to the 4th. Okay, based on how the last one went, I think, I'm not sure what's going to happen with that negative. If it's going to kick it back up and make it, you know, like a, or it's going to make it e to the negative 3 or something. I don't know. But maybe I should, no, I'm not. I'm going to say, all right, my integrating factor, we know, is going to be e to the antiderivative of p. Okay, and so that's going to be e to the antiderivative of negative 3 over t plus 1. Okay, yeah, and so, whoops. Okay. And then that's going to be t plus 1 to the negative 3. The e to the log of that was going to be t. Yeah. This is okay. And then I'm going to go and I'm going to say, all right, that's my integrating factor. So t plus 1 to the negative 3y prime. Okay. That'll be minus 3 times t plus 1 to the negative 4, because I already had 1 in the denominator, and then, you know, multiplying in 3 more is going to give me 4 total powers. And then when I multiply this over, yeah, that'll go, and I'll just have 1 power of t plus 1. Okay, this is the derivative of something. I've lost the y again, but definitely needed to have that. This is the derivative with respect to t of y multiplied by t plus 1 to the negative 3. Okay, so I'm going to anti-differentiate both sides, and I'll get y times t plus 1 to the negative 3 is going to be equal to 1/2 t squared plus t. Okay. And I'll solve for y plus c, pardon me. And then I think I'll solve for y by just multiplying both sides by t plus 1 to the 3. And that'll be good enough for us here. All right, next is going to be y prime plus 2 over ty. Y prime plus 2 over ty is equal to sine t over t squared. Okay, my integrating factor will be mu equals e to the antiderivative, or 2 times the antiderivative of 1 over t dt. Okay, so that's going to be t squared. Because this is log, the same thing that keeps happening, I'm going to, apply that power. It's just going to be t squared. Okay. Make me have t squared y prime plus 2t squared divided by t is 2t to the first times y equals, okay, well, if I multiply both sides by t squared, that's going to kill off that t squared, and I'll have sine t. Okay, so this is going to be the derivative with respect to t of y multiplied by t squared. Now I'm going to anti-differentiate both sides with respect to t. And divide by t squared. Something like that. All right, and so hopefully at this point you're going to start to see like, okay, these are very predictable. They pretty much work the exact same way every time, and you should start to feel more comfortable about this point, I would hope. And that's why I put 17 of them on there, so that, you know, if you're like, I feel like I still need a little more practice, promise you if you do all 17 of them, you're gonna feel confident in the integrating factor technique, right? So the next one, maybe I'll copy this one down the way that it's written. dy dx minus y over x is equal to negative x e to the negative x. Okay, so I think, oh yeah, it's gonna be, oh, maybe this one might have a little more excitement on it. Anyway, I'm gonna say, all right, my kind of p is this negative 1 over x. Okay. So my integrating factor is going to be e to the antiderivative of negative 1 over x. Okay, so that's e to the negative log x. E to the log x is just x, meaning I've got x to the negative first power. Yeah. Perfect. And so I thought maybe for some reason I thought that this was going to go in and make a second power of x, and then I was going to have to use UDV. And we could do that. That wouldn't be the end of the world. I think that I've heard people telling me that that's going to come up later in the problem set. So, you know, we'll be ready for that whenever that does happen. Anyway, now I'm going to say 1 over x dy dx minus, what's going on here, y over x multiplied by x to the negative 1, yeah, negative x to the negative 2, yeah. Wait, that's right. No, yeah, negative x to the negative 2, yeah, because that's the factor that I'm taking the derivative of, yes, of course, as you know. And then when I divide by x, I just get negative e to the negative x. Okay, now I'm going to say, hey, wait, this is the derivative with respect to x of y multiplied by 1 over x, right? Because I left 1 over x the same and took the derivative of y over here. And then over here I left y the same and took the derivative of 1 over x, which is negative x to the negative 2. Okay, this is the type of thing we might like to take the antiderivative of. So I'll have y times 1 over x equals positive e to the negative x plus c. And then I just multiply both sides by x to solve for y, and I'll say y is equal to x e to the negative x plus cx. So that's number 4. Is there going to be, I gotta think there's going to be enough room. Yeah, there's definitely going to be enough room for number 5. Alright, so this would be y prime plus 2xy equals x. Okay, p equals 2x. My integrating factor is going to be e to the antiderivative of 2x. So that's going to be e to the x squared. So y prime plus 2x e to the x squared multiplied by y is equal to x e to the x squared. Yeah. Okay. And yes, this, I can see what this is going to require u du. This is going to be a product rule derivative, right? I took the derivative of e to the x squared multiplied by y. It looks, I can see that. Okay. I don't know that I'm actually going to have to, go all the way through and do the full-blown u du here. I think that, e to the x squared should be your hypothesis, right? The derivative of that is 2x e to the x squared, so I think the antiderivative would be half of e to the x squared. But I mean, I can sit and check it. Okay, I'm going to anti-differentiate both sides. I know this one. This, I'm thinking that's going to be 1/2 e to the x squared. Yeah, because when I take that, the derivative will be half of e to the x squared multiplied by 2 and x for the chain rule. So yeah, that's what I'll get there. And then I'll just be plus e. And then I'll be dividing both sides by e to the x squared. Oh, that's interesting. And so y will be equal to 1/2 plus c e to the negative x squared, right, if I'm dividing both things by e to the x squared. Okay, that one was interesting. Worked out a little differently from the others. Number 6 would be dy dx equals, no, dy dx minus 2y divided by x. Did I not already do this one? I did plus 2y divided by x. Okay, so yeah, that's going to come out completely differently. Minus 2y over x equals 3x to the 3. Okay. Okay, yeah, so e to the antiderivative of p dx, that's going to be mu, and that's going to be, all right, e to the negative 2 antiderivative of 1 over x. Okay, e to the log x is just x, so this is x to the negative 2. I'm going to say x to the negative 2y prime minus 2x to the negative 3 multiplied by y is equal to, when I multiply that in, that'll be 3x. Okay, and that's a little easier to look at and see, oh, okay, that's the derivative of y times x to the negative 2. Okay, I'm going to take the antiderivative of both sides. Right, and then, hold on, I lost myself. 3 halves x squared plus c. Oh, wait, yeah, that's not it. This is going to be y multiplied by x to the negative 2. So I need to solve for y by multiplying both sides by x squared, and y will equal 3 halves of x to the 4th plus c multiplied by x to the 2. Right. Oh, number 7. Great. Sure how this one got mixed in. I think maybe when I made this problem set, I was thinking, okay, I'll start to mix in some that aren't integrating factor technique, that are, you know, kind of obvious, so that we would, no, not everything. Oh, yeah, because this one does fit the mold. Y prime plus 4y equals 0 is what it says. Okay, or something equivalent to that. Now, this, you know, y prime plus p of t y equals q of t. Well, if p of t and q of t are both a constant, then y is non-zero, then you might need to use the integrating factor. But either, you know, even still, I don't think you would. I think it's still separable. So what we're going to do is we're going to say this is the same as y prime equals negative 4y, and we know the solution to that is y equals c e to the negative 4t. Pretty sure if you used e to the antiderivative of 4 dt, that would be e to the 4t, and you would have that as your integrating factor, and it would, you'd get the solution, but it would be a lot slower than be like, oh wait, I know the general solution to y prime equals k times y is y equals c e to the k times t. So I think I'm just going to leave that one there. But then this one still looks pretty simple, but it will require integrating factors. So y prime minus 2y equals x. Yeah, that one needs integrating factor. So I've got p equals negative 2. And we know that our integrating factor is going to be e to the antiderivative of 2 with respect to t. And so that'll be e to the 2t. Or e to the 2x, pardon me. Okay, so I'm going to have e to the 2x y prime minus 2e to the 2x. Oh, whoops, I didn't, yeah. Negative 2, so it's going to be e to the negative 2, yeah. Okay, this is one that's going to require UDV. Okay, yeah, that's going to be a product that I'm not going to be able to use substitution for. Okay, now this is the derivative with respect to x of y multiplied by e to the negative 2x. I'm just going to take a second to verify that. Yeah, negative 2e to the negative 2x. And then that will be equal to x e to the negative 2x. Might need to do some work to figure out what the antiderivative of x e to the negative 2x is with respect to x, but that won't be too bad. Okay. I know that the integral of u dv is equal to u times v minus the integral of v du. So if u equals x and dv equals e to the negative 2x dx, and I know I want u to be x because I late algebra before exponential, so I need to choose u equals x. And du is dx, v is going to be negative 1/2 e to the negative 2x. So that antiderivative is going to be uv minus the integral of v, so plus 1/2 of the integral of e to the negative 2x dx. And that will be negative 1/2 x e to the negative 2x minus 1/4 e to the negative 2x plus c. All right, so I'm going to kind of just take the antiderivative over here. When I take the antiderivative of this, I'm going to get what's in red. Oh, now that's interesting because when I go and I multiply both sides by that e to the 2x to cancel that off, I'm going to just have, well, that's going to be gone, that's going to be gone. I'm just going to have c e to the 2x. Okay, so y equals negative 1/2 x squared minus 1/4 plus c e to the 2x. Okay. And I think that's going to be all for this video. I might, if there's time this afternoon, I might come back around and do it. But I'll come back and I'll do the rest of these integrating factor examples soon. This is a good selection. Thanks for watching.